I welcome you to this course. My name is Ruben Borg. I am a structural and materials engineer and associate professor at the University of Malta. I am principal investigator on the Resilience Horizon 2020 project. This presentation shall deal with the restoration of a degraded historic reinforced concrete water tower using advanced techniques which are based on ultra-high durability concrete and textile reinforced self-healing concrete. This presentation refers to the water tower restoration project, and we shall go through a number of topics. We shall first go through a description of the project itself and the research objectives. We shall then go through the historical documentation which is necessary for such a project. We shall analyze the restoration strategy. We shall discuss actions on the structure. We shall then go through the assessment of the existing structure at the inspections carried out, the non-destructive assessment, and materials and structural assessment. This shall be followed by an assessment of advanced materials which were employed in the restoration of the water tower. In particular, we shall look at ultra-high durability concrete and textile reinforced concrete. Then we shall go through the structural design. We shall discuss the monitoring strategy and sensor network systems employed in the project. We shall then go through the biological assessment, followed by an overview of the construction process, the advanced construction methodologies. Finally, the presentation shall be concluded through an overview of the technology learning platform, which is developed for this project. The project refers to the restoration of the water tower. It was constructed in the 1930s. It is about 15 meters high and the tank has a diameter of circa 10 meters. It suffered degradation over the years because of concrete carbonation and exposure to a marine environment in particular. It was repaired in the 1970s, and this presentation shall cover the restoration goals. Interventions include the application of ultra-high durability concrete and textile reinforced concrete to ensure the longer-term performance of the structure, together with the installation of a sensor network system to allow for the monitoring in the long term. There are a number of research objectives for the project. These include the restoration framework for the historic reinforced concrete water tower, a detailed assessment of the structure including non-destructive analysis, materials assessment, and structural investigation, an advanced finite-element model for the structural analysis, interventions including re-alkalisation and electrochemical chloride extraction, advanced restoration materials development, which include ultra-high durability concrete for the strengthening of the columns and the development of textile reinforced high durability concrete for the strengthening of shell elements, but also the installation of an advanced sensor network system for long-term durability monitoring and structural health monitoring of the water tower. The project therefore presents a unique opportunity for a comprehensive approach, in particular in interventions on industrial heritage structures in reinforced concrete. It covers the assessment of materials and structures, even using advanced technologies, non-destructive, non-invasive methods, the advanced testing of existing materials, including durability performance assessment, the development of self-healing ultra-high durability concrete and textile reinforced concrete based also on nano-additives, and also the development and installation of an advanced sensor network system for the continuous longer-term monitoring of the performance of the structural health of the structure. The research was led by the University of Malta with the support of the Ministry of the Environment of Malta, and also with the collaboration of the Planning Authority and the Lands Authority of Malta. The project is a pilot project within the framework of the Resilience Horizon 2020 project. We shall first go through a description of the project and the research objectives. On the left, you can see the northwest orientation of the water tower, and on the right, the south orientation of the water tower. In particular, one can observe the severe degradation on the south-facing part of the structure. The water tower is located in the inner part of the Grand-Harbour of Malta. In fact, it is located in an industrial area and within the premises of the public abattoir. The water tower consists of a number of reinforced concrete elements. The foundation supports 12 columns, which in turn support a ring beam. The water tank rests on the ring beam and includes a domed base, a conical structure, and a drum with an open top. The water tower serves as a proof of concept, which is provided through the design, building and monitoring of the pilot project under excess exposure conditions using ultra-high durability concrete, which is developed in the Resilience project. The project includes the retrofitting of the reinforced concrete water tower, which is considered as an industrial heritage structure in Malta, and includes also the monitoring in the long term, employing advanced sensor systems. The structure is severely degraded, and the advanced materials are employed in the restoration and strengthening strategy. Motivation for restoration. The reinforced concrete water tower structure was constructed in the 1930s in Malta within the premises of the civil abattoir to provide for the supply of water and the needs of the abattoir. It is a unique structure in Malta. It is located within the industrial area of Marsan, the Grand-Harbour of Valletta in Malta, and immediately close to the sea. The structure is at circa 15 meters high, with the diameter of the tank being circa 10 meters. It is known that the structure was filled with seawater when in operation. The structure exhibits severe degradation, especially on the south-facing parts. It is considered as industrial heritage due to the unique features. It is restored and monitored through the Resilience Horizon 2020 project and the Water Tower Restoration Project, led by the University of Malta. It was used for decades, with a repair or strengthening intervention recorded in the 1970s, which included repair to the base of the tank, consisting in a reinforced concrete shell element, a dome, and the enlargement through jacketing of 12 columns supporting the tank itself. At one point, it was not used any longer as a result of signs of severe degradation, in particular in the water tank on the south-facing parts of the structure. The structure shows severe degradation in various parts, in particular the south-facing parts of the reservoir, including the drum and the base cone, but also in the three ring beams at the water reservoir level, including the top, the middle, and the bottom ring beam. Degradation in the columns and also the repair executed in the 70s was also evident in the structure. The project required the setting up of agreements for collaboration and an authorization for intervention. An agreement for collaboration was signed between the University of Malta and the Ministry for the Environment and the Lands Authority. An agreement for support and collaboration was signed between the University of Malta and the Planning Authority. Planning permission was granted by the Malta Planning Authority, and the permit was granted for the restoration of the water tower. A detailed restoration method statement was submitted as part of the planning application process, describing the interventions for restoration. A public tender was issued for the restoration project, and the tender was granted in 2019, with works officially starting in March 2019. The tender was issued by the Ministry for the Environment, which is supporting the restoration of the structure. A management structure led by the University of Malta was set up for the execution and completion of the works. In the second part of the lecture, we shall look at historical documentation. Historical documentation is actually necessary when there are interventions on industrial heritage in reinforced concrete. On the left, one can see a 1940s photograph, aerial view of the Grand-Harbour, showing the civil abattoir with the historic reinforced concrete water tower. And you can also see archive drawings. Archive research is necessary to be able to document well and to better understand the structure and the materials employed in construction. The original mechanical equipment at the water tower is also protected as part of the restoration project. In the picture, one can see the pipework associated with the tank. During the restoration project itself, historic markings were uncovered dating from the 1930s, marked at the time of the construction itself. In addition, a detailed assessment of historic drawings of the drainage and water systems in the surrounding area was conducted to better appreciate the relevance of the reinforced concrete water tower. In this section, we shall look at the restoration strategy. The restoration strategy is based on a number of principles which are essential when intervening on industrial heritage structures in reinforced concrete. First, the documentation process, historical documentation of the structure. Second, the detailed assessment of the structure, which refers to inspection of the structure and appraisal, the preparation of a catalogue of defects and degradation mapping, scanning of the structure and 3D modeling, the non-destructive assessment and testing, sampling of materials and testing, and the assessment of the structure. Then there is the structural modeling and the analysis. The advanced materials development, including the ultra-high durability concrete and the textile reinforced concrete. The advanced restoration and repair interventions. The application of ultra-high durability concrete and textile reinforced concrete on the structure itself. The monitoring and sensor network system, which refers to durability monitoring, structural health monitoring, and environmental monitoring. And finally, the development of a technology learning platform. The water tower presents a complex case. The restoration strategy therefore requires both an overall approach, the overall analysis of the structure, but also an analysis of specific components and elements in the structure. In this section, we shall look at actions on the structure. As mentioned earlier, the water tower is located close to the sea, and therefore an analysis of environmental factors is necessary. In particular, the air temperature, humidity, wind, precipitation are being presented in the slide. Based on environmental conditions, the following possible exposure subclasses have been identified. XC3, corrosion induced by carbonation due to a humid climate. XS1, corrosion induced by chlorides from seawater, aerial marine, due to the proximity of the water tower to the coast, less than 90 meters. And one must note the degradation due to chloride transport and reinforcement corrosion, wetting drying cycles, and carbonation. The tank, which was filled with seawater in the past, and this contributes to the presence of chloride ions in the concrete. And the damage predominantly evident refers to spalling of the concrete, delamination, and scaling due to reinforcement corrosion. In this section, we shall look at the assessment conducted on the existing structure, which is necessary prior to any intervention for repair or restoration. So the documentation of historic records was a first important step. The appraisal of defects, including the creation of a catalogue of defects and mapping of defects, was another important step. And the mapping of defects itself was conducted in different stages to assess the performance with time in the period 2009-2019. Non-destructive tests were conducted on the structure, and destructive tests on samples extracted from the structure was also carried out, in particular on cores extracted from the structure and reinforcement from the water tower. With regards inspection and modelling, an inspection of the structure was carried out on different occasions using specialized platforms in order to reach all parts of the structure, including within the water tower tank itself, and this was done prior to the construction of scaffolding. An aerial drone survey was conducted also to create a 3D model based on a scan of the water tower for documentation, and a 3D CAD model was developed for the finite element structural modeling. This enabled the accurate measurement of the dimensions of the structure as built and as existing, and the preparation of detailed drawings and a refined 3D model for further documentation and also for finite element numerical modeling. The investigation conducted on the existing structure is complex. The table presents a summary of the investigations conducted in order to assess the structure, the material properties, and overall performance. The assessment includes the compilation of the catalogue of defects, mapping of defects over a period of time, and photogrammetry over a period of time, a drone 3D survey and model, sounding survey, Schmidt-Hammer survey, moisture meter survey, a cover meter survey, half-cell corrosion investigation, resistivity of the concrete, portable microscope for crack measurement and analysis of the surface in situ, thermal imaging using an infrared camera, surface porosity, ultrasonic pulse velocity, georadar investigation and ultrasound investigation, and ambient noise microtremor analysis. A grid referencing system was adopted in the study. This was essential for the dimensional assessment, the mapping of degradation, non-destructive testing, for sampling and destructive testing and its referencing, the microtremor investigation, the structural assessment and modeling, the biological mapping and assessment, and also for the sensor installation and setting up of the network system. Because of degraded parts of the structure, because of spalling and delamination, the reinforcement was exposed in various parts of the structure. This enabled the verification of the type of reinforcement in the structure, the location of reinforcement, the cover, and other details, which were confirmed by measuring the structure. Therefore, the investigation included the dimensional assessment, the assessment of reinforcement dimensions, location, and cover, and also the identification of any inserts and details within the structure. The mapping of defects was considered an important exercise to better understand the present state of the structure. It was conducted with reference to the ACI Guide for conducting a visual inspection of concrete in service and the ACI Guide for the identification and control of visible defects of consolidation on formed concrete surfaces. Degradation mapping of all the components and elements in the water tower was carried out in 4 phases over time, so as to assess rapid degradation and variations with time. In addition, the assessment of the effects of orientation of the water tower and prevailing winds was also carried out. In this slide, one can see some examples of the mapping of defects of various elements in the structure, with reference to the catalogue of defects. For example, on the left, one can see mapping of defects in the base, in the domed base of the tank, mapping of defects in the ring beam, and also on the right, mapping of defects in the drum of the tank. Further documentation of the water tower was conducted with reference to photogrammetry, to a drone survey, and eventually construction of a 3D model based on the drone scan which was conducted, enabling therefore recording and documentation of the existing state and defects on the surface of the structure. In the images, one can see various pieces of equipment which were used for this investigation, including the Schmidt-Hammer, the ultrasonic techniques, georadar, cover meter, half-cell, and other related pieces of equipment required for such analysis. The georadar investigation, as presented in this slide, was a very important step in the assessment of the structure. It enabled the identification of reinforcement, inserts, and other features. It also enabled the 3D mapping of reinforcement within the structure, which otherwise proved difficult to identify. The georadar investigation was conducted on various components in the structure, including all the columns and also all the shell elements. It enabled the mapping of reinforcement, the confirmation of section sizes, and detailing elements. Another non-destructive technique employed was the half-cell investigation. This was conducted for the assessment of corrosion potential of reinforcement in the structure. A cover meter survey was conducted for the entire structure in order to assess the location of reinforcement, the type of reinforcement, and its cover. The entire structure was scanned, and this survey enabled also the verification of structural details. A Schmidt-Hammer survey was conducted also for the entire structure. Various parts of the structure were analyzed using an ultrasound flow detector, and resistivity was also assessed for the entire structure. All the information gathered from the non-destructive assessment was mapped for the water tower in order to better understand the state of the structure prior to any intervention. The thermal imaging technique was employed on the entire structure using an infrared camera. This exercise enabled the assessment of the lamination and spalled concrete in the structure, with the laminated concrete having a different temperature than the rest of the structure. Besides the non-destructive assessment, a detailed investigation was also carried out on samples which were extracted from the structure in various locations. Reference was made to orientation, elevation, type of element, in order to assess further the material properties. Various samples were extracted during the course of the investigation, and these include detached spalled material from the surface, biological growths on the surface and within the tank reservoir for further biological assessment, core samples cored through the structural elements themselves, and also steel reinforcement samples from parts of the structure with exposed reinforcement. Besides the non-destructive tests presented, additional analysis was conducted on materials and structure. The table presents a summary of the investigations conducted in order to assess the material properties, the structure, and its performance. The cored samples were assessed with respect to the following: the concrete density, the depth of carbonation, the core compressive strength, the modulus of elasticity of concrete, ultrasonic pulse velocity, variation of chloride ion content with depth from the surface, from both the inner and outer surface, vacuum saturation porosity, mercury intrusion porosimetry, gas permeability, chloride penetration tests, including accelerated tests, and concrete petrography. The concrete core samples and the reinforcing bar samples extracted from the water tower structure were analyzed in order to determine the mechanical properties of the materials. The table on the left, the upper table, represents the compressive strength results obtained for the columns. In particular, it was observed that the reinforced concrete jacket constructed in the 1970s to strengthen the existing water tower had an inferior quality concrete than the original concrete in the structure. The second table represents the compressive strength of concrete in the drum, and the last table at the bottom presents the properties of the reinforcing steel. Therefore, the concrete core samples extracted were used in particular to determine the compressive strength, the density, and the depth of carbonation, and the reinforcing steel extracted was used also to determine the tensile yield strength of the reinforcement. Besides the testing for mechanical properties of the concrete, additional tests were conducted in order to assess the durability performance, in order to assess the direct and indirect durability parameters on cored specimen. Different samples were extracted with respect to elevation, that is with height in the water tower, with respect to orientation, and also with respect to element type, because there are different types of elements in the structure. It was, for example, noted that the maximum size of aggregate in the concrete which was extracted from the columns was larger than 4 samples extracted from shell elements, which had a smaller maximum size of aggregate. Following the assessment of materials for their mechanical durability properties, additional investigation was conducted on the structure. This consisted in a micro-tremor investigation. A Tromino 3G seismograph was used to measure ambient noise and vibrations. Various parts of the structure were assessed, and as indicated in the photographs, the Tromino was placed at different locations with height in order to measure the ambient noise. The modal behavior of the water tower, therefore, was analyzed using ambient vibration measurements. 20 minutes of ambient vibration readings were recorded on a 3-component portable seismograph, the Tromino 3G seismograph, at 128 Hz sampling. The measurements were taken at a number of points inside and also on the rim of the drum, as indicated in the images. The measurements were also taken at points on the sides and also at ground level for comparison. The images presented show the different locations selected for the analysis of ambient noise. In particular, on the left, one can notice the Tromino located at the top of the dome internally within the tank, but also along the sides of the dome. In the images on the right, one can see the Tromino, which is located on the upper ring beam of the tank, at the upper extremity of the water tower. For microtremor investigation, the H-on-V methodology is applied. The mean horizontal spectrum, basically, is divided by the vertical spectrum in order to give H-on-V ratio as a function of frequency. That is, the mean over all windows. For man-made structures, the peak frequency represents modal resonance frequencies. For the water tower modal behavior, results show a very consistent single frequency at around 2.8 Hz. The structure therefore appears to oscillate very rigidly at the fundamental mode, and this is indicated in the graph. In this section, we shall be looking at advanced materials which were developed at the University of Malta for the purpose of this research, that is, within the Resilience Horizon 2020 project, materials which were applied in the water tower project. We shall start looking at ultra-high durability concrete. The ultra-high durability concrete had specific characteristics. It was self-compacting, it included steel fibers, and it had self-healing properties. In fact, the self-healing properties were attained thanks to a crystalline admixture. In addition, however, 3 types of nano-additives were also used to enhance the properties of the material even further. In particular, nano-alumina, nanocellulose, and nanocellulose fibers were applied. The table represents the mix designs considered for the different mixes considered in the research. As one can see, the material includes cement, CEM1 52.5, silica fume, superplasticizer, water, different aggregates, steel fibers, the crystalline admixtures, and nano-additives, including the nano-alumina, nanocellulose, and nanocellulose fibers. The water-cement ratio adopted was of 0.33, and the water-binder ratio adopted was of 0.2. First, the material was developed as a self-compacting concrete. The ultra-high durability concrete was required to have self-compacting properties, and this was confirmed in the initial stage. In addition, this material is required to also have high mechanical properties, including compressive strength and material toughness. In fact, the compressive strength at 28 days in general was relatively high, exceeding the target requirements and reaching even beyond 150 megapascal. Ultra-high durability concrete, besides demonstrating high performance with respect to the mechanical properties, also needs to demonstrate high performance with respect to durability. This was demonstrated through different tests, in particular chloride ion penetration tests. On the left-hand side, one can see the test setup and the test results obtained for the ASTM C1202 standard test method for the electrical indication of concrete's ability to resist chloride ion penetration. In effect, the non-steady state chloride migration coefficient was also estimated from this test. On the right-hand side, one can notice the test setup for the determination of the non-steady state migration coefficient. In the center image, one can notice the chloride ion penetration front. The tests demonstrated a very high performance for all the mixes analyzed in the research. The ultra-high durability concrete analyzed for all mixes demonstrated a high durability. This was demonstrated both through the indirect durability tests and through the direct durability tests. The indirect durability test, that is the vacuum saturation porosity and also the mercury intrusion porosimetry, demonstrated for all mixes a high performance, a low porosity. In addition, the direct durability tests, in particular capillary suction and also chloride migration tests, indicated a trend towards improved performance with time and exceptionally high durability performance. As we have seen in the previous slides, different ultra-high durability concrete mixes were developed, including different nano-additives, and the relative performance of these materials was assessed. The material, the ultra-high durability concrete, was assessed with respect to fresh, mechanical, and durability properties. The research was conducted in order to be able to define the materials which will eventually be used and applied in the water tower structure. 4 different mixes were selected from the previous investigation and were analyzed further in much more detail. These mixes are presented in the table on the left for ultra-high durability concrete, which refer to a reference ultra-high durability concrete mix with crystalline admixture, ultra-high durability concrete with nano-alumina, an ultra-high durability concrete with nanocellulose, and an ultra-high durability concrete with nanocellulose fibers. These 4 mixes were selected, analyzed, and eventually applied in the water tower structure. In addition, refinements and development of a textile reinforced concrete mix was conducted, and a mix was selected in order to be studied in more detail and was eventually applied in the water tower structure for the shell elements. Therefore, the mix selection criteria was the following: the performance of the fresh concrete, the mechanical properties, the durability performance, the ability to produce the material on the construction site, and also the ability to cast the ultra-high durability concrete and the textile reinforced concrete as required in the structure. The ultra-high durability concrete and the textile reinforced concrete were developed for their application on the water tower structure. On different parts of the water tower structure, the ultra-high durability concrete, as a self-compacting material, is applied to the reinforced concrete columns of the water tower, as indicated in the blue box in the diagram. On the other hand, the textile reinforced concrete is applied to the shell elements of the structure, to the drum, to the conical structure and the dome. In addition, it must be noted, the ultra-high durability concrete, the different mixes of ultra-high durability concrete, the 4 mixes, which include different types of nano-additive, are applied to different columns on different orientations of the water tower in order to assess the performance of this material with time, therefore to compare the performance in different orientations with time. Following the development of the ultra-high durability concrete mixes at the University of Malta and their selection for application in the water tower structure, a detailed assessment was conducted for the performance of the ultra-high durability concrete as a confining material for jacketing of concrete elements. The research was conducted and various variables were considered, including the geometry of the columns, having cylindrical and rectangular columns, the surface treatment of the concrete before the application of the ultra-high durability concrete, including the blasting of the surface and also the application of an epoxy resin on the surface. In addition, another variable considered was the application of load on the central core of a traditional concrete as against the application of load on the entire section of the elements. The analysis was conducted with respect to cylindrical specimen and also rectangular specimen, and rectangular specimen with chamfered corners. The analysis indicated a very high performance in terms of jacketing effect of traditional concrete elements. The ultra-high durability concrete had an exceptional performance, increasing considerably the capacity of the columns when axial load is applied. In addition, the bonding effect between the traditional concrete and the ultra-high durability concrete was also analyzed in detail. In the images, one can notice the pull-off assessment test, but also a detailed assessment conducted on the surface roughness of the material as part of the study. An additional study was conducted at the University of Malta for the development of a textile reinforced concrete and its detailed assessment, in particular with respect to the tensile and flexural properties of the textile reinforced concrete. In the study, 2 different types of carbon fiber textile were examined in order also to identify the best solution to be considered for the water tower structure. The results obtained indicated a high performance with respect to both tensile and flexural properties of all materials. This section refers to the structural design. Having analyzed in detail the materials properties, the existing materials in the structure and the structure itself, and having developed advanced materials to be applied in the water tower structure, the structural analysis is required, and it is based on the finite element modeling in order to obtain stresses and deformations in the structure. So, on the basis of the properties identified, different finite element models were created and analyzed in different phases. There was a preliminary analysis, a detailed preliminary analysis, modeling using SAP 2000, and eventually modeling using Abacus. Modeling using SAP 2000 was conducted with respect to different configurations. For example, modeling of the structure as built originally and modeling of the structure in the damaged state. The damaged state including loss of section in different parts of the structure, including the loss of section in parts of the drum and the conical structure, for example. In addition, different load configurations were considered, including the tank empty or the tank full of water. Through the modeling, the horizontal and the vertical forces in the structure could be determined as indicated in the images. Respectively, horizontal forces in the tank on the left and vertical forces in the tank on the right. This slide presents the horizontal bending moment with respect to the sub 2000 model. The image on the left presents the vertical bending moment diagram. The capacity domain before and after damage is presented in the image on the right. Before damage, that is for the structure for the reinforced concrete water tower as originally designed and constructed, and after damage for the reinforced concrete tower having lost part of the cross-section of the reinforced concrete because of the damage. In addition, detailed modeling was conducted using Abacus. The finite element modeling took into consideration also the damaged structure. And in addition, the requirements for strengthening were defined with specific solutions, as we have seen, that is, with respect to different parts of the structure. In particular, two types of ultra-high durability concrete were used. The self-compacting ultra-high durability concrete with steel fibers that was employed for the jackets of the columns, and the textile reinforced concrete, which was employed and used for the shell elements, that is, the drum and all other curved elements. The present slide presents the characteristics of the concrete considered. In addition, it presents the material modeling with Abacus with respect to finite element modeling using Abacus. Some of the parameters in the model are presented in this slide, and in addition, the steel mechanical characteristics are also being presented. The input in the model included not only the concrete and steel properties, which were obtained through the assessment of the materials in the structure, as explained earlier, but also the dimensional properties of the structure, including the thicknesses of the concrete, and also the disposition of the reinforcement in the structure, that is, the reinforcing bars in all the elements, including the shell elements and also the reinforced concrete columns. As part of the input parameters in the model, a peak ground acceleration of 0.095 g was considered. A dynamic analysis was carried out considering an accelerogram and also with the tank filled with water. Therefore, the water hydrostatic pressure considered within the tank. The accelerogram is presented in the diagrams. The model was used also to analyze the interventions using ultra-high durability concrete and textile reinforced concrete in order to model the behavior of the structure once repaired with these advanced techniques. Therefore, in the model, the strengthening of the columns was considered on the basis of ultra-high durability concrete jackets with fibre-reinforced concrete, 2% dosage of fibers and a thickness of 2 centimeters, and with an ultra-high durability concrete having a compressive strength of 150 megapascal. In the case of the shell elements, carbon-reinforced textile mortar was considered. The material considered has a thickness of 20 millimeters with a mortar compressive strength of 100 megapascal. A bidirectional fabric is considered, and the materials were modeled in this structure in order to assess the overall performance of the repaired structure. We have seen, therefore, that the finite element model enabled us to model the structure with respect to the material properties, to the geometric characteristics and reinforcement disposition in the original structure, but also with respect to the interventions using advanced materials, the jacketing of the columns using ultra-high durability concrete, and also the application of textile reinforced concrete to the shell elements. Different load configurations were considered, and the structure could be analyzed in order to determine the performance of the structure once it is repaired. In this section, we shall go through the monitoring and sensor network system. Different sensor types are considered for installation in the water tower structure through a high-level sensor network system. These sensor types are mainly split into three groups. First, sensors for durability monitoring, sensors for structural health monitoring, and environmental sensors. The location of the sensors is determined on the basis of various parameters, including the structural assessment and finite-element model. This refers to the stress distribution in the structure, but also, in the case in particular of the durability sensors, the orientation, site conditions, and also different structural elements and geometries. Different types of durability sensors were installed in the structure. The durability sensors include galvanic pairs, resistivity sensors, embedded reference electrodes, and platinum thermometers. They are presented in the images. The plan on the right-hand side indicates the disposition of the sensors on different parts of the structure in order to measure the performance of the structure with time, with respect to orientation, but also with respect to different elements within the structure. A number of sensor stations were identified and located in different parts of the structure. Here they are represented on 4 elevations, representing the 4 main orientations: north, south, east, west. At each sensor station, 4 different types of sensors were installed, as indicated earlier, that is, galvanic, resistivity, embedded reference electrodes, and temperature sensors. The durability sensor system, therefore, which we have just seen, refers to different sensors which are installed at stations which are distributed in different parts of the structure, also with respect to different orientations, to measure the performance with time of the structure and different components within the structure. In addition to that, a structural health monitoring system and an environmental monitoring system were installed. In the case of the structural health monitoring system, the sensors included are the vibrating wire, concrete-mounted surface strain gauges, joint meters, inclinometers, and accelerometers. With respect to environmental monitoring, a weather station was installed to measure humidity, temperature, and dew point. The image on the right indicates a plan showing the different locations for the sensors in the structure. The 4 elevations represent the 4 main orientations, and the different sensors are installed in different locations in the structure, indicating the structural health monitoring system. The durability sensor network system, therefore, consists in different sensors, in particular resistivity, galvanic pair, embedded reference electrode, and temperature sensors, which were installed within cores which were extracted from the structure and which were eventually reinstalled and reintegrated in the structure, as indicated in the images. The durability sensors were prepared at the University of Malta and assembled in the cores which had been extracted from the water tower. Once assembled, the cores with the sensors were reinstated and reintegrated in different parts of the water tower structure, including the columns, the conical structure, and the drum, as indicated in the images. In addition, some of the sensors were installed directly on the reinforcement of the structure prior to casting of the concrete to reinstate the section. This section refers to the biological assessment of the structure. Now, this is an important assessment because it provides important information about the state of the structure about its past use. This information is also important to better understand the performance of materials, as we shall see. In the case of industrial heritage structures, as in the case of the reinforced concrete water tower, one needs to appreciate the performance of the structure with time. A lichen floristic study was carried out in order to identify the typical species making up the lichen patina on the 20th century water reservoir located in the civil abattoir. In addition, some findings of conchological material which is found inside the reservoir is also presented. The assessment of the composition and distribution of the lichen communities is influenced by the orientation, but also by the inclination of the surfaces, and also the height from the bottom towards the top of the structure. The presence of lichens is also a reflection of the base material, of the base concrete. The sampling techniques considered include direct samplings from the structure and also systematic quadrat sampling technique. The methodology adopted therefore refers to the systematic quadrat technique. It refers to frames for different areas. It refers to a photographic assessment, analysis of the species composition and relative abundance, and recording of the environmental data, including the aspect, inclination, and elevation. In addition, laboratory analysis was conducted, including analysis on material deposition. Routine lichenological methods were applied, including microscopic techniques and also microchemical tests, which were performed in order to identify the species. For the conchological analysis, the sieving of the debris inside the tank was adopted and microscopical analysis was conducted on the material in order to identify the species. The global lichen species diversity could be defined. The outer surfaces of the water reservoir were in fact colonized by 11 predominant species of lichens belonging to 7 genera, as indicated in the table. In fact, the lichen present an interesting indicator because they relate to the aspect, to the inclination, that is vertical or horizontal, as well as to different structural elements and their exposure. In fact, different communities could be identified, and these communities could be related to the base material, to the concrete. Common lichen species on horizontal and vertical exposed surfaces could be identified, as indicated in the image. On the other hand, different communities were observed on vertical shaded locations, such as the west and the north-facing parts of the water tower. In addition, dominant species could be identified adjacent to exposed metal, that is, where concrete had spoiled, exposing the reinforcement of the water tower. Therefore, lichen frequency and diversity analysis could be related to aspect. In fact, species can be presented with respect to growth form, inclination, orientation of the structure in relation to the base material. Therefore, one can conclude that lichen growth is related indeed to the structural geometry, but also to the base material. When considering lichen frequency with height, it was noted that lichens varied with respect to vertical surfaces with height, reflected also in different colors and structures of the lichen. In addition, lichen mapping was conducted. This was conducted in order to assess the covered areas and their distribution for further detailed analysis related to the environment and orientation, height in the structure and exposure, the base material properties, that is the concrete properties, and other related factors. Therefore, using lichens as an important indicator of the structural state. A conchological analysis was also conducted, since in the tank there were various growths on the concrete surface. These growths demonstrated various past uses of the water tower, including possible filling in of the tank with seawater or brackish water. This analysis provided important information on major mollusk species identified within the tank, and this is also indicative of past uses of the tank and how it was filled in with water. The different species identified within the tank are also related to biological zone preferences, therefore related to the water used to fill in the tank over the years. Through this study, therefore, the different species which were identified within the tank could provide important information on past uses of the tank. The biological assessment, therefore, the results obtained confirm the importance of considering biological inventories, of considering biological assessments in historic structures, especially when a physical change, such as a restoration project, is going to take place. In this particular case, the study of organisms has been used to provide information on the type of existent environment in which the structure was built, and also to provide an inventory of the 20th century biota present in the area. This study is very innovative because it refers to industrial heritage in reinforced concrete. Most importantly, from a conservation aspect, it has provided an opportunity to preserve specimens of species of an environment that has become extinct throughout the years, such as is the case the gastropods, which are remnants of the Marsa marshland, and also in the case of lichens due to the restoration works on the water reservoir itself. Furthermore, the study confirms past uses of the structure, which provide important information in the strategy for restoration of the water tower. This section refers to advanced construction, that is, the methodologies applied in interventions in the restoration of the reinforced concrete water tower. Therefore, advanced construction is based on various actions applied as part of the comprehensive interventions on the water tower. These include the construction of replica structures for the assessment of materials and methods, the erection of temporary structures, the removal of detached delaminated concrete, the removal of past restoration interventions, application of sandblasting and surface preparation, application of electrochemical chloride extraction and re-alkalisation techniques, patch repair, epoxy injection in concrete, temporary supporting structures, reinstatement of reinforcement, reinstatement of the concrete itself, and the application of ultra-high durability concrete jacketing to columns, and the application of textile reinforced concrete to shell elements. The project and construction management aspects are particularly relevant for such an intense, comprehensive project. With respect to site management for restoration, reference must be made to the project management, construction management structure, to the setting up of a detailed quality assurance, inspection and quality control system, the coordination of contractors, subcontractors and the research team, this being also a research project, detailed documentation of the activities and processes, the health and safety monitoring, restoration monitoring by the authorities, and coordination with the authorities managing the abattoir. In addition, advanced material preparation station is necessary. This refers to the sourcing and storage of materials on site, the adequate selection of a concrete high shear mixer for the production of the concrete, and the setting up of a site mix preparation station close enough to the water tower structure. The construction of replica structures, which included replica columns and replica shell wall elements, was considered as a very important step. This exercise allows for the application of materials and technologies on replica structures prior to the effective application on the water tower structure itself. This exercise included the production of replica columns based on dimensional assessment of the structure, materials analysis based on the testing of concrete cores extracted from the water tower and reinforcement in the structure, replicating the drum curved wall elements based on dimensional assessment, materials analysis, including assessment of concrete and reinforcement in the structure, and eventually the trial testing of the new materials, including the 4 different ultra-high durability concrete mixes used with respect to fresh hardened properties, including also pull-off testing, but also the assessment of the textile reinforced concrete on these replica structures. The replica structures therefore referred to replica columns and replica walls, which are presented in the images. The concrete used reflected the concrete used in the structure, and the mixed design for each of the 2 types of elements is presented in the table. The replica structures were used, therefore, for the application of ultra-high durability concrete in the case of the columns, and for the application of textile reinforced concrete in the case of the curved shell element. The materials, once applied, were tested for different properties, including the pull-off performance, therefore assessing the bond between the original concrete and the ultra-high durability concrete applied. One can observe a comparative assessment between different phases of a column, an exercise which was conducted in order to assess the effective bond characteristics between the original concrete and the ultra-high durability concrete, which is cast. Therefore, assessing a cast concrete surface, an epoxy-coated surface, and a rough sand-blasted surface. Therefore, comparing 3 different types of surface finishes. Indeed, the replica structures were also used in order to test the sensor systems which were employed, in particular the durability sensors, which were produced, manufactured and procured at the University of Malta, and which were embedded in the trial replica structures in order also to assess their performance with respect to field conditions. The interventions on the water tower were various. These include re-alkalisation and electrochemical chloride extraction, the application of epoxy resin injection to stitch cracked elements, the application of glass fiber reinforced anchored elements to enhance bond, the reintegration of reinforcement, the application of a corrosion inhibitor onto the existing structure, the application of polymer-based non-shrink repair cement-based material, the application of waterproofing within the tank, and also the application of ultra-high durability concrete for the strengthening of the columns and the application of textile reinforced concrete for the strengthening of the shell elements. Temporary structures were also considered important. In particular, temporary structures were set up as safe scaffolding systems in order to provide access to all parts of the structure, including within the tank itself. In addition, supporting structures were necessary to support the tank from below, under the arches. An important exercise consisted in the removal of spalled concrete and the removal of delaminated concrete. For this exercise, handheld tools and light mechanical equipment had to be used in order not to damage further the structure. One must note that the thickness of the drum is of 15 centimeters. With loss of half that section, only circa 7 centimeters of concrete remains. In addition, the corroded metal inserts were also removed, as were also the reinforcement bars, which were detached and heavily corroded. Cores were also extracted in specific cases, in particular for the installation of sensors. A number of past repair interventions were noted in the structure. In specific areas, patch repair was observed. In addition, repair of the concrete columns had been conducted in the 70s using a reinforced concrete conventional concrete jacket with a thickness of circa 75 mm. The jacket was found to consist of inferior quality concrete, and the jacket itself, being so thick, had altered significantly the appearance of the water tower. The jacket was removed using handheld mechanical equipment, as can be seen in the images. Following a detailed investigation of the bond characteristics between the ultra-high durability concrete and conventional concrete surfaces, a particular approach was adopted whereby the surfaces were prepared using sandblasting. This was adopted in order to get a sufficiently rough surface for adequate bond between the ultra-high durability concrete and the original concrete, or between the ultra-high durability concrete and the reinstated conventional concrete in the tank structure. In addition, removal of past repair interventions on the tank elements was also implemented. Following the assessment of chloride ions in the existing concrete, electrochemical chloride extraction and re-alkalisation techniques were applied. These were applied within the tank structure of the water tower. Electrochemical chloride extraction is applied to reduce chloride contamination and passivate active corrosion. Re-alkalisation is a non-destructive treatment which is applied to increase the pH of carbonated structures and passivate active corrosion. Electrochemically treating a reinforced concrete structure has the potential to reduce corrosion susceptibility in the following ways: by reducing the chloride content in the concrete, the permeability of cracks by electrodeposition of insoluble products, the concrete permeability by altering the pore size distribution and forming a tightly adherent deposit on the treated surface. Both systems are applied to a structure on a short-term basis for long-term results. Each system can provide different levels of corrosion protection and cost. Limitations for both are similar. The cathodic reaction indicates that by providing electrons to the steel, new hydroxyl ions may be generated at the steel surface, and this restores the alkalinity and increases the pH value. Note that by using sodium or carbonate electrolyte, the treatment provides future resistance to carbonation. Remarkable results have been reported in marine environments in particular by extending the service life of the structure. Therefore, this technique was applied in particular on the interior parts of the structure, interior parts of the tank. Patch repair techniques were applied to the columns. The existing reinforcement was thoroughly cleared of detached and spoiled concrete and was thoroughly cleaned from rust deposits, as indicated in the image. A corrosion inhibitor was applied to the exposed, cleaned reinforcement. And eventually, a polymer-based cement repair mortar was applied. Patch repair techniques were applied also to the shell elements of the water tower structure. The detached and spoiled concrete was first removed. In addition, the reinforcement was cleaned from rust deposits, following which a corrosion inhibitor was applied. A polymer-based cement repair mortar was applied, and the original geometry of the elements was applied again on the structure. Epoxy injection techniques were applied for crack sealing, in particular in the shell elements of the water tower structure. This approach was based on important steps, including the identification and opening of all cracks on the shell elements, the sealing of cracks on both sides of the shell elements, as indicated in the images, drilling of holes for epoxy injection, and then epoxy injection to stitch detached elements. Because of heavy degradation on the south-facing parts, the drum shell elements had lost half of their cross-section. That is, the original 15 centimeters ended up at just 7 centimeters. The corroded reinforcement and the detached concrete were removed cautiously, leaving a thin 7 centimeter concrete structure as indicated in the photographs. The cracks between the elements making up the structure were thoroughly sealed as indicated in the images, and epoxy injection was applied in order to stitch these fragmented parts of the structure. This was considered as a very delicate job in order to guarantee the integrity of the original remaining parts of the structure. The images presented show the application of epoxy injection for the sealing of cracks within the thin shell elements in the water tank. In order to guarantee the stability of the tank during these operations, a temporary supporting structure was installed within the tank, in particular in preparation for the reinstatement of the section, that is, the reinstatement to the original 15 centimeter thickness. The installation of new reinforcement, substituting the corroded and detached reinforcement which had been removed, was necessary. This was installed replicating the original reinforcement also at mid-depth of the section in the drum shell element. Following the epoxy injection to seal cracks, the strengthening temporarily of the shell elements from within the tank, the application of reinforcement to reinstate the reinforcing of the shell elements, the application of a normal concrete was applied in order to reinstate the original 150 mm thickness of the drum shell element. This was particularly relevant on the south-facing elevation of the water tank. Ultra-high durability concrete jacketing was applied to the columns. This exercise refers to the mixes developed and discussed earlier in this presentation. The application of the ultra-high durability concrete depends on various steps, including the preparation of the ultra-high durability concrete mixes and their application on the replica structures, the assembly of formwork including details based on the chamfers and other details to respect the original 1930s design, the application of the self-compacting ultra-high durability concrete as jackets to the columns, eventually the curing of the concrete, shrinkage control and measures for hot weather concreting, typical in Malta, and eventually a quality finish, detailing and including, in instances, imprints in the cast to mark specific items. The 4 different ultra-high durability concrete mixes were respecting the mix design presented earlier, a thorough quality assurance and quality control regime was applied, including the testing of fresh properties of the ultra-high durability concrete, but also the thorough assessment of the mechanical properties of the material, including the mechanical and also the durability performance of the concrete. The images indicate the jacketing applied and completed on the reinforced concrete columns at the water tower in the civil abattoir. As described earlier, the repair of the reinforced concrete columns therefore consisted in the application of ultra-high durability concrete, which was applied at a thickness of 20 millimeters throughout the columns from top to bottom, including also the replicating of the original details in the original 1930s structure. The interventions include also the application of the ultra-high durability textile reinforced concrete repair to shell elements. This material is based on a carbon textile mesh and the application of the mesh in conjunction with a ultra-high durability concrete with a high viscosity. The mesh is also applied at a thin thickness of 20 millimeters throughout the shell elements as indicated in the images. This section refers to the Innovative Technology Learning Platform, which refers to the application of innovative materials, to the application of innovative technologies and techniques to industrial heritage structures in order to guarantee their lifetime performance. The degradation of reinforced concrete structures exposed to an aggressive environment, to an aggressive marine and coastal environment, present a challenge. Equally challenging is the restoration of industrial heritage exposed to aggressive environments. Advanced materials and advanced technologies are well placed to present the right solutions, the optimum solutions in these cases. In particular, ultra-high durability concrete with self-healing properties for application in such cases. The water tower project, the reinforced concrete water tower project, presents an opportunity for the creation of the technology learning platform in advanced materials performance, structural health monitoring, and industrial heritage conservation, particularly because of the continuous monitoring thanks to the sensor network system developed in the project. The technology learning platform is based on public-private entities and also academia. In fact, the water tower project itself already includes the participation of different partners, of public-private entities and of academia. Indeed, it serves as an important resource. It is serving as a teaching tool, as a training tool, but also for research purposes and surely for academic industry collaboration. It serves indeed as an important platform for innovation. The project presents important outreach for e-learning. It presents advanced materials, sensor network systems, and structural health monitoring for the conservation of industrial heritage. It presents an opportunity for sustainability of construction in aggressive environments, and surely for the resilience of civil infrastructure. I would like to thank you for your attention to this presentation. This presentation was intended to present the case study of the reinforced concrete water tower, including the necessary investigation of an existing structure and then the application of innovative materials based on ultra-high durability concrete with self-healing properties and innovative technologies for the application on existing structures and infrastructure. Thank you for your attention.